Okay, we are starting chapter 6 today. We're going to go through about half of it, finish it up on Thursday. We are talking about reactions of alkenes. We're going to focus on about 7 or 8 of them. And what I want you to be paying attention to is I don't want you to just try to memorize which thing is doing which. Okay? Remember in, I think it was chapter 4, when we were talking about the acid-base reactions and the electron movement is now what we're looking at. What I'm noticing is that several of you are just trying to kind of memorize what's happening. You're not understanding what the electrons are doing. And that was clear from 2 of the test questions. So now we're getting into it more. You have to understand those pi bonds, the sigma bonds, what electrons are going from where, electron rich versus electron poor entities. Okay? So we're going to introduce all the different kinds of reactions. We're going to talk about them, define some definitions. And then next week, or I'm sorry, Thursday, we'll finish up chapter 6. Okay? So when we talk about reactions of alkenes, the most common reaction you're going to see is addition reactions. So basically, when we talk about addition reactions, we are talking about literally adding something to something else. And we're going to talk about it in terms of, chain growth. So we might have a double bonded alkene that we're going to saturate it, it's no longer going to have a double bond, and other things are going to be added to it. Might be a hydrogen, might be a hydroxide, might be another carbon chain. It just depends, okay? So when we talk about this, what we're talking about is taking this pi bond here, of the 2, and having those electrons go and attack something else that it's going to add in order to saturate the unsaturated carbon chain, and by way of adding something to it. So first we're going to talk about these, and then I've written out detail for detail examples for each one of these, okay? So we're going to have your hydrohalogenation. They write it here hydrochlorination because they're specifically using HCl, okay? But what we're saying is HX. Any of the halogens will form this here. Hydration, addition of water. Bromination or halogenation. In this case, they called it bromination because you're using Br2. And you'll note that bromination is very, very popular when it comes to the halogens. But it can be Cl2, it could be F2, it could be I2. Bromination is just the most popular one you're going to see. Then there's bromohalohydrin formation, where we have not only the hydrogen, but also the water. I want to explain one more thing because you're going to see me write this both ways. Typically, in your book, what you will see is our standard setup for writing a chemical equation. Reactant 1 plus reactant 2 gives you your product. However, I often, and you will see this in many places, will write number 2 on top of the arrow. Okay? It means the same thing if it's on top of the arrow and not here. Okay? Okay. It means the same thing. If it's below the arrow, it is either an active or inert solvent that if it's inert, meaning non-reactive, it doesn't play a role in the reaction. If it is active, it does play a role in the reaction. And you're going to see that when we get to, for example, this one here. Here, if I were to write this, I would be writing Br2 up top and the water below. Okay, if I were just doing the second reactant over the arrow. And what that means is water, in this case, is not inert. It is active. Therefore, it plays a role. And that's where we're getting the hydroxide and the bromine from. Okay, make sense? Okay, you guys are going to get hundreds? We're good? All right. Okay, some more. Oxymercuration, hydroboration. I'm going to save these. I'm not going to talk about these today. I'm going to talk about these on Thursday. But oxidation and reduction, oil rig that y'all have in your head, get rid of it. It means something completely different in organic chemistry. When we're talking about oxidation, we are talking about the addition of hydroxides. When we are talking about reduction, we are talking about the addition of hydrogens. Okay? So it's not that redox isn't a thing. It is, but we're going to leave the oil rig definition for Gen Chem. Okay? In organic, I want you to know that oxidation is hydroxide, reduction is the addition of hydrogens. And if you think about oil rig, oxidation is loss, right? What did we say happened when we had a new bond form? That electronegative entity, it was actually kind of giving up electrons a little bit to form that new covalent bond, right? So in a way, yeah, that's oxidation. Reduction, hydrogen is gaining an electron by formation of that covalent bond. Okay, so the rules still apply, but just know in here, oxidation is the addition of hydroxides, reduction the addition of hydrogens. I remember it because oxidation starts with an O, and we're adding the hydroxide, which is the oxygen. Okay? All right, so now I'm going to flip over to my notes. It's a lot for you guys to write. I thought about uploading it, and then I just didn't. Sorry. Okay, so the wording here and the understanding here is a little bit different. What I want you to do for right now, take a minute, write down the name in the box and the structures I have written, okay? These structures, just all the structures and the words in the box. Okay, just take a minute and do that. And then that way you can write notes on it as we go. What I will do today is I will scan this as a PDF and I will upload it and I will scan it in color. All right, and I will put it under probably like miscellaneous folder or something. So you'll have it. I know it's a lot. And I wrote really neatly. Just wanted to mention that. And I tried to keep the exact same reactant in each one, just for ease. Say again? Okay. Yeah, don't worry about all the words around it. Just focus on the box and the structures for right now. And there's about 3 pages of this stuff, just so you're aware. Yeah. I promise you I'll scan it and upload it. I also recommend tonight when you get home, and this will help you to remember these things, go ahead and on a separate sheet of paper, just all the reactions that we do from this stuff, just write it out and keep a running list of the types of reactions, okay? And to have that handy when you're doing homework, you know, working problems, that kind of thing. All right, are we good? No? Okay, sorry. Hydrogenation. 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 Hydrohalogenation. Yep. Those are the only two on this page. All the structures. Hold off. I mean, if you haven't written them already, you can hold off on this because I don't know how much you're going to need for room. Yeah. But we're going to talk about each piece of this. I mean, if you can fit it, it's better to, because this all is related. So if you can fit it all together, that would be best. If you can't, put it on another page.
So like on your reactant side, you see how like all the way on the right it has like the hydrogen and it's like half as old.
Oh, on the right. I'm going to talk about it. Just copy what you see, copy down, and then we're going to talk about it. Okay, we good? Yeah? All right. So let's talk about this. I'm going to start and I'm going to blow this up a little bit, okay? All right, is that good? Can you see it better? All right. So when we talk about hydrogenation, we are talking literally about the addition of H2. I've written this, like I told you, on top of my arrow. That means it's a reactant. On the previous slides we were just looking at, what you would have seen was this structure plus H2, then the arrow. I have a tendency to flip-flop, but I mainly use this format. Okay? Just know it means the same thing. Top of the arrow is your reactant. Bottom of the arrow is your either catalyst or active or inactive solvent. Okay? Active meaning it will participate. Inert or inactive meaning it will not participate in the overall reaction. Okay? Now, many of these organic reactions are what we call stepwise reactions. There's more than one step involved. Okay? The reaction mechanism, or the mechanism in which it does the steps and in what order, determines often what your product is going to be and how things become attached to get rid of that pi bond. All right? So some of these have multiple steps, some of them don't. A reaction mechanism can only be determined experimentally. All right? So what that means is when you determine it experimentally, you think you might have a reaction mechanism and you have to test each step of the way to see if what your product is at the first step matches what you think it might have been. And eventually we get pretty much standard accepted mechanisms, reaction mechanisms. But as we learn more and gain more knowledge, sometimes those can change, be altered, or just be completely thrown out and replaced by some other reaction mechanism that's generally accepted. All right? So for this case, when we talk about electron push, if that electron push from the addition of something creates a carbocation or a radical, it's a stepwise reaction. So the formation of that carbocation or radical first means there's got to be a second step involved to get rid of that plus sign on the carbon. Okay? So when we look here, what we're going to see is that what we really have is the diatom HH in this case, hydrogens. And what's going to happen is these hydrogens are going to come in. They are going to break this pi bond. So what we get is these electrons going in and attacking a hydrogen. The electrons go back to the other hydrogen, okay? And it'll break the bond. And then a second step will come in and the other hydrogen will attach. We refer to this as syn, a syn attachment, S-Y-N. I'll talk about syn and anti more on the second page because it has to do with positioning. Syn sounds like same, it is, but when we're talking about syn and anti, we're talking about dashes and wedges as opposed to opposite side. Okay? All right. So this is the hydrogenation. Pi bonds are broken. They're relatively easy to break. They come in, attach, and this is going to be your final product. And this is generally done in the presence of a palladium catalyst. Sometimes it might be platinum, but generally the most common is palladium. And that's what acts to start the process of those pi bonds breaking, making those electrons available to bond. Okay? So it has a role, but it doesn't participate in the reaction in that it doesn't attach itself to anything in the reaction. Okay? All right. Your hydrohalogenation, we're going to do two comparisons, well, a couple of comparisons here. What you would normally think is that if this were going to come in, it's going to break these pi bonds and attach here, just like we saw up here. This, however, is a special case. So let's just talk about it generically first, then we'll talk about the special case. So when we're talking about standard conditions, what we're saying is, according to Markov rule, a hydrogen that is present will attach to the carbon that is less substituted, meaning it has more hydrogens than the other carbon. Okay? So if I just think about here, I'm going to draw it generically. If I'm just looking at that right there, those two carbons where the double bond is, you have a carbon, double bond carbon, there they are, right? So the question is, when this is broken, well, where does the hydrogen go and where does the chloride go? Does it matter? The answer is absolutely 100% yes, it matters. So this carbon right here is attached to a carbon, attached to a carbon, attached to another carbon. This carbon, I'm ignoring these hydrogens because I don't care about them. This carbon, the only thing it's attached to is two hydrogens. Okay? So when we're looking and saying, well, gosh, this, you know, hydrohalogenation, my hydro, there's my hydrogen, my halo, okay, my halogen, which goes where, what's happening, we would think that, again, yes, this pi bond is going to be broken, okay? And I want you to think about HCl in terms of what's happening. So hydrogen and Cl, although they're both nonmetals, when we have two nonmetals and we're thinking about partial positives and partial negatives, we're going to look at electronegativity. So the Cl will have that partial negative, and the H will take on the partial positive because chloride ion has a much higher electronegativity than does hydrogen. Okay? So when you're thinking about that, what's happening is this is coming in and attaching a hydrogen. And we would think then, because of Markov's rule, that the chloride ion goes here because it's this carbon that you can see that is less substituted. It has more hydrogens. They're not substituted with carbons. This one clearly has way more carbons, way less hydrogens. So the electronegative one, let me just rephrase that. Hydrogen will always go to the carbon that has more hydrogens. It wants to be with its buddies. Okay? You would think we would get this. The problem is we don't get that. This does not happen. We get a hydride shift. Hydride shift. Huh? Okay. Think about this. When this first hydrogen gets attached, if you go through and draw out all the electron push, you will see that this carbon here, this sp carbon, becomes a carbocation. You'll get the plus on it. Okay? Why? Because electrons are shifting, and to form this bond now, remember, becomes plus because it formed a new covalent bond. Here is your rule. If there is an sp2 carbon directly next to the sp carbon that is a carbocation, that means it's an intermediate. So what does this really look like? I'll draw it over here. In this stepwise reaction, that's what we will get. Okay? Because this is an sp2 hybridized carbon, right next to the sp, there is a hydrogen here. Remember, in this format, we don't write it. Okay? This hydrogen will shift to that carbon, giving us this. Okay? This is the intermediate step of the first step of the reaction. Then what's left when that happens is I got this negative chloride that's going to come in and actually attach where that new carbocation is. Okay? Make sense? You want me to say it again? Yeah. Okay. When the pi bond is broken, hydrogen attaches. We do not get this though, because as soon as that first hydrogen attaches, this becomes a carbocation, a plus side. I think I said side, I meant to say sign. Plus sign. When that happens, we get a hydride shift. The hydrogen that is here that we don't really write in this line angle format goes and attaches. I wrote a Cl here. That was supposed to be a hydrogen. Sorry. It'll shift. Sorry, that was my bad. I did that yesterday. It shifts to here, where we would think the chlorine would go. And it does that in order to take care of the carbocation that was formed right here. Okay? Now, once we took care of this carbocation, it caused a positive to go here. But that's okay. It's okay because it's sp2 hybridized. And so now that's the only spot the chloride ion can go. Okay? So we would think that, well, gosh, we should get that. That's not actually what happens because we get that hydride shift. This occurs when there's an sp carbon that becomes a carbocation and it's next to an sp2 hybridized carbon. Okay? Questions? If you have questions, now is the time to ask. Or do you just need to stare at it for a minute? We're getting there. We're working it. Okay? Okay. Now, here, it's a little bit more detailed. Now I've switched to bromine, hydrobromic acid. Okay? Still the same structure, still the same structure we've been using. What I have here is, again, I want you to think of your HBr in this format. It matters because you have to decide what's going to hold that partial positive and partial negative. Okay? So this is broken. This pi bond is broken. And the electrons come in and bond to the hydrogen. This causes a carbocation here, and this hydrogen follows Markonov's rule that says, all right, hydrogen goes to the carbon that has more hydrogens, not more carbons. Okay? But again, there is this sp2 hybridized carbon directly next to this carbocation. So we get a hydride shift, which causes, here, it's shifted, which causes that there. Okay? That shift occurred because it's more stable for an sp2 hybridized carbon to be temporarily a carbocation than it is for the sp to be that carbocation. Okay, this carbon right here that became the carbocation when I attached the first hydrogen, I mean, it's only got 2 bonds right now. It's not stable. It's not going to work. It won't stay that way. So that hydrogen will shift. Okay, it shifts to here, making this your carbocation. So this is step 1. Then the bromine comes in and attaches there in our stepwise reaction. I don't want you to memorize these. I want you to understand what is happening. Okay? Questions about this? Is it making a little bit more sense? A little bit more clear? Some of it is, you just need to stare at it. Your book, I meant to bring the book today. I just left it on my counter when I walked out of the house. But your book in this section has lots of examples. Okay? I will also try to find a couple of videos to upload for you guys so you can take a look at those as well. Work the problems. Yes?
So when you're doing the reactant that you put above the yolk, so like the hydro and the boron, right there, so you're basically having to distinguish which one is partially negative and positive electronegativity?
When they're both nonmetals, yes. If it's a metal and a nonmetal, then you have your permanent positives, permanent negatives, etc., because one's a metal, one's a nonmetal. But yeah, if they're nonmetals, you're looking at electronegativity values, because the one that's more electronegative is going to hang on to those more closely. If you guys just write this down, if you remember from Gen Chem, the range, if it's less than 0.5, it's nonpolar. If it's 0.5 to 1.7, it's polar. Anything above 1.7 is ionic, as far as the difference of electronegativity values. Okay? All right, so now, oh, sorry. All right, and again, I am going to scan this in color and upload it for you guys. Okay, you good? Everybody else good? Can I change pages now? Okay. All right. Oh, yes, there's more. Let's roll. All right. So now I'm going to talk about hydrohalogenation in not standard conditions. What we just saw was standard conditions. Now we're going to talk about the exact same reaction in not standard conditions. So for not standard conditions, hold on, I'm just going to focus on this part. I'm going to zoom in right here. Not standard conditions, we're talking about radical conditions. Peroxides, extreme heat, extreme light. Radical, not standard conditions. Okay. 2 things you will notice about my product. You should notice immediately there is no hydride shift, no proton shift, and Markanoff's rule is not followed. You'll note the hydrogen is on the more substituted carbon, and that is not Markanoff's rule. We would expect to see the hydrogen here, the bromine here. Okay. Again, I just want to reiterate my reactant and the conditions or solvent it is in. I wrote ROR, some kind of peroxide of some kind, just a generic formula for that. If it was extreme high heat, I would either write an extremely high temperature or I would write high heat or something like that. Okay? But you need to know that these are those conditions. What we get here, no hydride shift and does not follow Markov. We almost never see this. It's not common. And it's not common because 95, more than that, most reactions are done under standard conditions. Questions about this one? Yes?
What is Markov's rule? Is that just what we were doing earlier?
That's with the rule of the hydrogen. The hydrogen goes to the side, the carbon that has more hydrogens. So we would expect to see that hydrogen here, but it's not. Okay. It's going to the more substituted carbon. Right. But again, that's why we barely see it. And there's no hydrogen shift. There's no hydride shift. If there had been a hydride shift, write down what you think this would look like. If there was a hydride shift here, write down what you think the final product would look like. Oh, that's a highlighter. That's not going to work on my board. All right, you got down what you think it might look like? Okay, I'm going to put the answer out. You get it?
Yes.
Yay! Okay. When do we do the hydride shift? 1 second. When is the time we do a hydride shift? Okay, so we have to have 3 things happen. We have to have an sp2 hybridized carbocation. Directly next to it has to be an I just said sp2, I meant to say sp. We need to have an sp carbocation. Directly next to it, we need to have the sp2 carbon so it can give the hydrogen to stabilize that sp. And then we need to have formed this carbocation to begin with, meaning it's stepwise. The reaction mechanism is stepwise. Okay? Yes. 3 things that have to happen. First, we have to form the carbocation on an sp hybridized carbon. We got to have it there. Second, it has to be directly next to an sp2 hybridized carbon so that your hydrogen can shift to stabilize the sp carbon. Okay? Those 3 things have to happen. All right? And then you know it's stepwise, it's a 2-step reaction. Okay? All right. Now, yes. Oh, I'm sorry, I forgot you had one. Yeah.
So for that top one, the not version,
Mm-hmm.
only when it's like heat involved.
Radical conditions. Extreme heat or light, a peroxide, extreme pressures, extreme conditions, right? And pretty much everything we do, like if you're just in a lab carrying out reactions, by definition of being on the earth in a lab, it's standard conditions, right? You know, you're at standard temperature and pressure, you have standard room temperatures, you know, we're not talking about crazy scenarios, but sometimes we do have to do, well, we don't have to, but we can do crazy different situations. Like you can control that in a lab setting, okay? All right, so halogenation. So this is where we just get some sort of halogen in its diatomic form added, okay? And we're going to talk about it in terms of halohydrin. We're going to compare and contrast the two. You will notice that halogenation is just simply some halogen in its diatomic form with some inert solvent, meaning there's some solvent there that does not participate in the reaction. In halohydrin, still get our diatomic halogen, But now we have some sort of reactive or active solvent that does participate in the reaction. Most of the time, it's going to be water. But not all of the time. So I want you to think about water instead of being H2O. I want you to think about it, hold on, I want you to think about it and draw it like HOH. Get rid of one hydrogen and attach the rest. Why does this matter? Because what if it's methanol? CH3OH, right? CH3OH. Get rid of an H, add what's left. Okay? Y'all still with me? Okay. Now, this is going to be an anti-attachment. It's anti, again, when we say anti or syn, we're talking about dashes and wedges. If it is syn addition, then they're either both dashed or both wedged. If it's anti, you're going to have one or the other. One is dashed, one is wedged. Okay? So, and here we have the same thing that applies. This pi bond is broken. And because Br and Br are both the exact same thing, their bonds are nonpolar. So it's not really going to matter which bromine is, you know, attacking first or is attacked first, right? But it's going to come in and attach, and we're going to get here this attachments, these attachments. Now, the reason why it's anti, one would be dashed, one would be wedged, is because of configuration and strength. Okay? Now, if we look at halohydrin, halo meaning your halogen, hydrin meaning hydroxide of some kind, oxygen of some kind, all right? What we get is they both participate. So here, a bromide ion is added, only one of them, even though it's Br2, but that's okay, because remember, when we break things apart and we write a chemical reaction, we're only writing the representation of one thing happening when there's billions in the solution, okay? So a bromine will attach, and now, remember, HOH, get rid of a hydrogen, add what's left, the hydroxide gets added, okay? However, this is Markov because hydroxide has the greater electronegativity. So now that we don't have hydrogens to say, oh, hydrogens want to be with the one that has more hydrogens, the rule we follow is the more electronegative one gets the more substituted carbon. Or what we say is less hydrogen side. Okay? The more electronegative one gets the carbon that has more carbons attached to it. Or less hydrogens. Okay? Questions about this? The only difference between these two is this one has an inert solvent that doesn't play a role in the final product. This one has an active solvent or reactive solvent that does participate. Okay, yes?
Why does one of the hydrogen on each example get taken out of it?
Because that's the rule and trick I'm giving you. Yeah. Yes? Down or up? Good. When you see this and a reactive solvent underneath it, generally a reactant solvent is going to be something polar. Think of that reactant solvent in this format where we write the whole thing out, drop the hydrogen, add whatever is left. Okay?
Whichever one has a higher electronegativity goes
Correct. Meaning less hydrogens are present. Okay? If we have a hydrogen, then the hydrogen gets the hydrogens. Okay? And that should make sense also, because if when we looked at HBr, right, we saw that hydrogen had that partially positive, and the other thing was the partially negative one. Okay? Yeah, yeah, okay. Okay. Do you mean on the arrow? My right or your right? That just had to do with, oh, okay, I didn't, don't think of it that way. No. What it means is they're basically going to be trans. And again, it has to do with strain and all of that involved. So, I mean, bromine is huge. And oxygen is pretty large as well compared to these carbons and hydrogens that are present. And if you put both of them down here, remember, they are still both electronegative, right? It's kind of like when we have the lone pairs of electrons on water and then the hydrogens are repelling each other, the lone pairs are repelling, and you know, we kind of get this bent shape from that. Effectively, it's the same, except this is going to be up and down. Remember, it's this anti, so we still have to pay attention to dashes and wedges. Okay, but they effectively will be trans. Okay, we good? Can I go to the next one? I think we only have two more pages. I think it's this one. Nope, just kidding. 3. Okay. So here we have an acid catalyzed hydration. And what I mean by acid catalyzed hydration is just like what it sounds. It's a hydration. And when we say hydration, you'll probably remember this from biology, especially when you talked about carbohydrates and sugars and all that and glycosidic bonds. We generally use hydrogens to break bonds, meaning pi bonds. So we have a hydration here with water, and it's acid catalyzed, which generally means you'll see something like this. You'll see, you know, hydronium ion, some kind of acid, H2SO4 in some way, shape, or form, water, etc. Something along those lines. It means add a hydroxide when you see that. Okay? So, what's going on here? Well, when you add a hydrogen and this bond gets broken, okay, you are going to get a hydrogen added, and that's going to cause that carbocation to form. So what happens? We get a hydride shift because there's an sp2 hybridized carbon directly next to it that has a hydrogen that shifts to stabilize this. Okay? That means the plus sign is now here. So in step 2, when the hydroxide is added, it's going to be added to that carbon. Yes? Because this could be, this is going to be catalyzed by an acid. Like I said, it could be this, it could be this, it could be this, it could be H3PO4. What that means is add a hydroxide. It's an acid as opposed to just H2. Or here, oh, because this has the halogens involved. Hydroxide is not a halogen. Okay. Because this was, oh, sorry, there. Okay, because this is a reactive solvent for the same reason in the next one we're just talking about. That's what catalyzes it. That's what drives it to go. Remember the very, very first one we did, we had palladium, and that's what started the process of breaking down those pi bonds. In this case, we have an inert solvent, but these are just halogens. Now, the only thing we're dealing with is some kind of acid that's going to catalyze the whole thing and make this and break that double bond and add stuff on. I know they all look identical. I know they all look like we're basically doing the same thing 100,000 times. But they're completely different. A distinction with a difference, but not much of a distinction. Okay? So here, and also with this one, the water's on top, meaning it's the reactant. But again, it could have been H3O plus or H2SO4 or, you know, some sort of other acid, which simply means an OH. Add an OH. Okay? So because of the hydrogen added, we get that carbocation. So the hydride shift occurs. And then the hydroxide that's added actually goes on the second carbon. Okay? Yes?
Just double check. If the acid is below the arrow, then
It's a solvent.
doesn't have to shift.
It depends on what's on top. Whatever's on top is going to determine, because that's the reactant. The one on top is the reactant. So if the reactant adds a hydrogen first, then there's going to be a hydride shift.
Okay, so that's again. Right.
First, because that's what causes the carbocation. Okay? All right. So now our oxymercuration, this no shift, okay, because it happens simultaneously, so there's no shift, there's no intermediate, one step. It does follow Markov, where our hydrogen gets added to the less substituted carbon, and our hydroxide goes to the more substituted carbon. Okay? Our alkoxymercuration, now we're talking about an alkaline of some kind. Oh, sorry. Yep. There you go. Now, this is going to be anti, so we have to consider dash and wedges. One will be dashed, one will be wedged. Okay? And then some kind of alkyl group will be attached. And in this case, I just gave a generic example of mercury OAC2. And then we have this solvent of NaBH4. Okay. I could have written this above the arrow, and it would mean the same thing. Instead of writing plus blah, I could have just written it up here on top of the arrow. If I want to clarify something, pay close attention to this. If you have a plus something and then something written above the arrow, that acts as either a catalyst to drive the reaction or some kind of solvent it's in. Okay, when you have a plus something and something on top of the arrow, this is not really, I don't really think of this in terms of reactant. It may be reactive, but it is not necessarily a reactant. It participates in some way. And depending on what is above that arrow tells you what it is. Generally, if you see metals, those are usually the catalysts, generally speaking. Okay? And those metals that are catalysts are going to be by themselves. Palladium, platinum, sometimes iron. Okay, they're going to be all by themselves in their standard state. Okay, so here, again, you're going to follow that same rule. Write it as, and I just did a generic alkyl group. Just ROH, right? Drop the H and add whatever's left. Remember, R is our generic carbon chain. Okay? So here, we get our oxygen that attaches, whatever carbon chain that is. We're not paying attention to the carbon chain. But remember, just like the example on the previous page, we said this, right? This would be our R group, and that's just, of course, your O and your H. Drop a hydrogen, add whatever is left. So if this example were this, that's what I would have. Yes.
What was the reasoning again to use the rule drop the hydrogen? Like, how did you guys do it on this example today?
Because I immediately saw what was there. If it's ROH and I see this and some other carbon group attached to it, that's an alkyl group. The rule is the same. Okay? I know this is a lot. I know it's a lot. Work problem after problem after problem after problem after problem. And if you've gone through all the worksheets and want more problems, email me. I will find a worksheet and upload it with a key. Okay? Your homework for the next exam on this stuff is going to be critical for you to do well on the next exam. So much so, I would spend more time studying this than the other stuff. Like, if you're going to divide your time up, spend a lot of time on this. A lot of times working a lot of problems. Okay? All right, other questions about this before I flip pages? Oh, we're running out of time. Okay, so now we have hydroboration. We're going to see this a lot. So generally what you have is, first and foremost, you have a BH3 and THF as the solvent, okay? And then the second part of it is you're going to have typically sodium hydroxide, but usually just, a base, a strong base. And either some sort of other thing going on, a peroxide, a water, an H3O plus, something to that degree. And what we get here is a syn addition. These would either be both wedged or both dashed. Okay. You will note that it is, here it turns and shifts, as I've shown you, into anti, meaning basically trans, but opposite wedge and dash. One would be wedge, one would be dashed. At this point, I don't expect you to know which is which, or like when it does which. But if I give you a structure, and one is wedged and one is dashed, I would expect you to know that it's anti. If I give you either both wedged or both dashed, I would expect you to know that it's syn addition. Okay, so by looking at a structure, I would expect you to tell me what's happening, or what it is. Describe it to me, okay? So when you have the same face, this is important, write this down, star it, highlight it. When you have the same face, meaning the whatever it is we're adding comes in on the same face, we're going to get syn addition. So both are dashed or both are wedged. The part of when do they come in on the same face, at this point, I don't expect you to understand yet. Okay, we'll get there eventually. So here we have marking off, it follows it, but not marking off, right? So you would think we would get this. You would think we would get this. Right? Hydrogen, more hydrogens, more electronegative, goes to the more substituted side, but we don't. Therefore, something like this is not super common. You'll note all the things we had to put in here in order to get this outcome. It's not necessarily extreme conditions, but there was a lot of work that had to get put into it. Okay. I'm going to skip epoxidation, putting alkenes into epoxides. I just want to explain to you, just so you've seen it, a couple of things. All right. We may go back to it on Thursday, but for right now, I'm just going to talk about, you don't even have to write this down. I just want to show you. So basically, epoxidation is just taking an alkene and converting it into epoxide. which only means the oxygen is shared between the two carbons where the double bond would be. So basically, this oxygen is directly bonded to this oxygen is directly, I said oxygen, carbon, and it's directly bonded to this carbon. Those are the two carbons involved in the double bond, okay? And that's what it looks like. It must be syn addition. There can't be anything else, because the one carbon is both directly bonded to the one oxygen is directly bonded to two different carbons. So there's no way it could be anti or opposite, because it's all linked together, okay? So here's an example here where you could come in and just say, okay, well, I'm going to put it back into this position. But again, I'm not going to worry too much about epoxidation right now. Just know that when we turn an alkene into an epoxide, it simply means adding an oxygen that is shared between the two carbons involved in the double bond. Okay? I know it looks a little weird, but just because it looks weird doesn't mean it's wrong. All right? Okay, and for this, I'm going to stop there. I'm going to do more of these on Thursday. I'm not stopping there for the class. I'm just stopping there for my writing. I will upload this for you today, but it won't be till later, because I'm just not going to be home to do it till later. And then when I finish writing out more, I'll scan those and I'll upload those as well. Okay, so you can print those out and bring them and then just write on them as you go. Okay? Okay, this is in your PowerPoints. I recommend going through this. And if you take it out of slideshow mode, in the notes underneath, when these examples are up here, the answers are in the little notes section. Okay? All right. So when we talk about stepwise reactions, which we've talked about now several times, what we're talking about is understanding that there's one step and two step, and just like with every other reaction, if it's exothermic, the products have a lower energy than the beginning reactants, right? That's the whole point of being exothermic and to react at all, because it's more stable for the products to have a lower energy than the beginning reactants. This is true also of two-step reactions, but each step has its own energy of activation. Okay, so step one has some energy of activation, some calculated amount. Then you get the intermediates that will go ahead and react in step two, and it will have its own energy of activation. And in the end, the products have a much lower energy than the reactants. Now, I am not going to require you to know and calculate, not to know, but to calculate any of the delta H's that are involved here. I do expect you to have it just as a generic understanding, right? So when we have negative delta H's, it's an exothermic reaction. Most of your reactions here, well, not most, but a lot are going to be exothermic. Negative delta H, exothermic. Positive delta H, endothermic. How do I remember that? Because endo means going into, adding in positive delta H. Exo means going away, like money in your bank account, negative delta H. Okay? Here, I just want to show you that you can calculate it, just like you can every other delta H for every other reaction. But this right here, you need to understand this point. This is exothermic because stronger bonds are made in the product than compared to the reactants. It is also lower energy of the products than compared to the reactants. So your rule of thumb is when it's exothermic, your products have stronger bonds and less overall energy than the reactants. Okay? Your rate determining step, that's the slow step, You'll remember this from when we did those stepwise reactions in Gen Chem. Remember doing all that? What's your rate determining step, the slow step? Well, then what is the rate for the overall reaction and finding K and all that product over reactant stuff, all that fun stuff? I'm not going to ask you to calculate that in here. You just have to understand it generically. So the other thing you need to highlight, star, asterisk, whatever, this right here. When we talk about transition states, we're talking about that point of transition. That's where you will see those intermediates. They are peaks on the energy surface, and the chemical structures, there's no measurable lifetime. How long do they last that way? There's no way to really measure how long it takes for that transition to actually finish and complete. We just know there is a transitional state. So when we're developing reaction mechanisms, here's the takeaway. They're constantly changing as we learn more stuff, as we figure out more stuff. Sometimes we just tweak our reaction mechanism. We might do that to, I don't know, have a better yield. Sometimes we'll do, you guys have done this when you try to figure out your yield, like what you got, and you're like, oh, it's only 20% of what I started with or what I should have gotten, right? That's a really poor yield. So you might have, you know, and in your lab journals or lab reports or whatever it is, you always say, well, if I had done this differently by doing X, Y, Z, perhaps it would have been, you know, a higher yield. If I dried it longer, if I reacted it to completion, etc. You always tweak those little things. With reaction mechanisms, we do the same thing. Some things that it's just normal to only get about 50% yield on really, really expensive stuff. So tweaking our reaction mechanism, if we can get another 5% yield, that might be saving hundreds of dollars. Okay. Also, these reaction mechanisms are helpful because when we have a reaction mechanism, for example, for one alkene, we can predict how similar alkenes will behave as well in a similar scenario. Just like we know, for example, all group 2 metals bond with oxygen in a 1-to-1 ratio. We know that to be true. Likewise, we can say, oh, if this alkene is going to behave this way with this reaction mechanism with something, then another alkene that's similar, we should expect to see the same thing happen. Okay? I like this. Is funny. Where is it? Why do chemists go to the trouble to establish them? Intellectual satisfaction. I just think that one's kind of funny. All right. So again, I just want to remind you on electron movement and electron pushing. We use the arrow, the curved arrow. You'll note here that we have a double arrow versus a single arrow. That's just representing 2 electrons are going versus 1. Up to this point, I haven't really talked about that too much, but we use a full arrow if it's 2 electrons, a single arrow if it's 1. Okay? If you recall also, this part of the arrow is showing from where the electrons are coming. The pointed end is to where they are going. And I should never, ever, 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 ever see it go from some element that clearly has no lone pairs of electrons attacking the oxygen to bond. That's not what's happening. The lone pair of electrons from oxygen are coming in and attacking that hydrogen, and by doing that, the electron in the bonds are going back onto that oxygen. It's getting them back. That's why we get the negative sign and the positive sign. How much time do I have? Okay, I'm going to do this and the next slide, and then we're going to be done. So we have an electron source or an electron-rich entity, and then we have an electron poor or the electron sink entity. Okay? So what does that mean? That means one is going to be the nucleophile, one is going to be the electrophile. The nucleophile is the electron rich. The electrophile is the electron poor. It's electron loving and therefore wants the electrons from something that has a lot of them. Okay? So here, if we look at this, This oxygen clearly has a lot of electrons comparatively compared to this carbocation, which is short electrons. This carbocation is going to behave as the electrophile, and it's right now this is an intermediate because it's not stabilized. It's going to behave as the electrophile because it is electron poor. It's missing electrons, needs them. So it's going to be the electron sink, the sink in which the electrons are dumped. Okay, so this nucleophile or electron-rich oxygen is going to come in and attack that carbocation, giving us this. But now that this covalent bond is formed, oxygen takes the plus, which is okay because it's now sharing with that new covalent bond, but it now has an octet, and so does the carbon. Okay, oxygen doesn't love having a positive, but if it's going to have a positive and everything has an octet, we're good there. All right? Okay. I'm going to talk about patterns. Oh, I missed a slide. I have to update this and re-upload it because I missed a slide. There should be a pattern 1 slide. So we're going to talk about patterns on Thursday and more of Chapter 6. Okay, as soon as I'm done finishing the PowerPoints for Chapter 6, I'll upload it in a part 2. And we'll go from there. I will see you guys Thursday.